Welcome back to Unit 2 of our course. Now this is Lecture 6. And in this lecture, what we'll try to do is talk about this electron density. That is, so far you see, we haven't quite brought in the electron density into the discussion very much, because when we talk about the ballistic conductance, conductivity, the expressions we had involved density of states, it involved number of modes, but didn't quite involve this electron density. And what's electron density? Well, the way you can think about it is, if you had a band with a density of states like I've shown here, and if your electrochemical potential were somewhere here, then at zero temperature, what would happen is, all the states below the electrochemical potential, that's mu, below that would be occupied. So how many electrons would we have? Well, it would basically be whatever many states you have below mu. So, and what does n tell us? This n, it tells us how many states are actually there whose momentum is less than p. Whereas what we want to know is how many states are occupied. And of course, all states below mu are occupied. So what you could do is actually use that function to obtain the electron density. Let me explain a little further. So this is the total number of states. Now, if you want electron density, then you usually talk about number of electrons per unit length, or per unit area, or per unit volume. So what we could do is take that capital N and divide by L in 1D, divide by WL in 2D, or divide by AL in 3D. And so you'd have this function, which you could call electron density, N. And it's exactly that function, except that I've left out the L and the WL and the AL. So this is what you're left with. And from this, how could I find out the number of this electron density with a given electrochemical potential? Well, first step would be get your energy momentum relation, so you can convert the P into a E. That will then give you kind of electron density as a function of energy. And then at 0 Kelvin, of course, all the states below E equals mu are filled. So what does this function tell you? Well, it tells you the electron density you'd have if all states were filled up to E's, because this tells you the total number of states per unit volume that you have whose energy is less than E. So at 0 Kelvin, if I put E equals mu, I'll get the correct number of electrons, the electron density, I guess. Now, so this is fairly straightforward if you think about it at 0 temperature. In that case, the function we have been discussing, this comes back from lecture 3, that itself will give you the electron density. Now, what we want to talk about is, how do we do this when T is not equal to 0 Kelvin? That when it's at a reasonable temperature, I mean not at 0. Because then, as you know, the states are not occupied. We cannot quite say that the states below mu are occupied and above mu are empty. They are occupied according to this Fermi function. And the Fermi function well below mu is 1, well above mu is 0, and it changes in between over an energy range of the order of kT. That's something we talked about early in Unit 1, if you remember. In fact, this picture of the Fermi function, this is the equilibrium Fermi function. I guess I should have written F0 here. This is the equilibrium Fermi function. This I have taken from one of the Unit 1 lectures. Now, if you wanted to calculate the number of electrons, what you should do then is N0, number of electrons, would be like D, density of states, times F0. Density of states tells you how many states you have per unit energy. F0 tells you, the Fermi function tells you if the state is occupied or not. So if you want the number of electrons, then you should take the number of states and multiply it by whether it's occupied or not. So that's this. Now what's D? Well, that's the derivative of capital N. So you have dN dE times F0. Now what you could do is, there's a bit of algebra, you can integrate this by parts. That is, you have two functions here, N and F0. the derivative is on the first function. But there is this trick of integrating by parts, whereby the derivative, instead of being on the first function, is transferred over to the second function. So if you do that, you'll have first what you call the surface term, that is n times f0, whose values at the two limits you need, minus infinity and plus infinity. And then you have the other term, where you see the derivative is now gone from n, and instead it appears on the f0. And there's a minus sign associated with it. So here we had dn dE times f0. Now we have n times minus df dE. Okay. Now this term is 0. Why is that? Well, look at the two limits. Consider first the positive infinity. Well, positive infinity means very large energy. That's where you can see the Fermi function is 0. So f0 is 0. So nf0 is also 0. Well, what about minus infinity? Well, because that means I'm at very low energies. Now, of course, f0 is not 0, it's 1. So I can't ignore f0. But the point is, the n of E, that function is 0 down here, because it kind of starts at the bottom of the band. That's where it starts growing. So this quantity then is 0 at both limits. Doesn't matter what it is in between. What is needed here is the value at the two limits, and they are both 0. So you drop it. And so you're left with that. And this kind of, you can visualize that you have a function n of E, you see whose derivative is that function, d of E. So this is the integrated version of that. And the thing is, how do you find the number of electrons? You can take d, multiply by Fermi function, integrate. Or you could take n, multiplied by the derivative of the Fermi function, and integrate. And those are the same thing. This is mathematically the same result as that. See? And here the point is that when you go to very low temperatures, then of course this df dE kind of becomes like a delta function right at that energy. And so when you integrate, you basically get the value of n at that energy, which is what we talked about in the last slide, that at 0 temperature, the electron density is simply given by the value of n of E at mu. Whereas if you are at non-zero temperatures, what you need to do is average this n of E over a certain range of energies determined by this df dE. Okay. And you'll notice here, you see, that how similar it is in general with the way we think of conductance or all the quantities we have been talking about. They also involve this average over energy in the same way, using this df dE function. So what we could do then is, this is this expression we had for n of P. If you take states per unit volume, you get the small n of P, and then you can combine it with the energy momentum relation to get an n of E, and then if you average it over energy, you'll get n0. And this is in spirit much like what we have been talking about with conductance, for example. So conductance also involves this average, and usually we have been talking about this function, and usually I have not been carrying around this integral everywhere. But G of E is like the conductance at a given energy, and it's understood that anytime you want actual values, you should multiply by df dE and average, like you're told here. And then we're talking about this G of E, that's determined by this ballistic conductance and the mean free path. And the ballistic conductance itself has this expression of density of states times velocity, or the number of modes. These are all functions of energy. But finally, of course, if you want a measurable quantity like the conductance at a given temperature, you'll have to average. So same here now. We now have an expression, a quantity n of E here, which tells you the electron density. And the understanding is, at 0 temperature, the electron density is just whatever n happens to be at E equals mu. At non-zero temperatures, you have to average. You see? Okay. Now, before finishing up this section, I'd like to point out one little subtlety with respect to bands that run downwards. That is, this discussion is fairly clear and straightforward, like what we just went through, when the band runs upwards like this, that there is a bottom of the band and energies are available above it, and there is nothing below. On the other hand, think of a band that is running downwards, where there is an upper value that's often written as EV for the valence band, and the energy momentum relation runs downwards. As I mentioned, that's quite common in solids. That's what you usually have in the valence band. And now if you have a electrochemical potential mu, then the point I'd like to make is that this N of E that we discussed will actually give you the number of states above mu and not the states below mu. That is, it will essentially give you what you call the number of holes, that is the empty states. That is, N0 is actually not integral of density of states times the Fermi function, but rather it's density of states times 1 minus the Fermi function. Fermi function tells you whether a state is occupied. 1 minus F tells you if it's empty. So this quantity, what I'd like to show you is, this is what our N of E will give you. That is, let's say we define it this way. Then for density of states, then we write dN dE, except that now we need a minus sign. Why is that? Well, because you see, now when you talk about N of E, what it represents is all the states whose energy is higher than E, because momentum is 0 right here. N of P tells you how many states have a certain, N of P tells you how many states are available below a certain value of P, and that corresponds to how many states are available above a certain energy E, you see. So you have an N of E that is actually increasing as you go down in energy. What that means is density of states is kind of like the negative of its derivative. So that's why I wrote a minus dN dE. And now you can do this integration by parts again. That is, and you'll get these two terms. There'll be N times 1 minus F0, and then there'll be another term which will be N times dF0 dE. So this is exactly the same integration by parts that we did in the last slide. But one very important point I want to make is that this N times 1 minus F0 is a quantity that vanishes at both ends, so you can actually ignore it. On the other hand, if I had started with F0 instead of 1 minus F0, then I would have got NF0 over here. And NF0 would not be 0 at one of the limits, which means I wouldn't be able to ignore this term. So whatever I did here only works if I use 1 minus F0. Doesn't work if you use F0. Because, as I said, when you go to very low energies, you see, F0 is 1. And N is still increasing, you see. So N is not 0. Not like the previous case where I could say that when you're at very low energies, N is 0, and so NF0 is 0. So here NF0 is not equal to 0. But N times 1 minus F0 is, because down here F0 is almost 1, so 1 minus F0 is 0. So I can drop that term. So finally, of course, what you're getting then is that this quantity, our capital N averaged over energy here, will actually give you the number of holes in a band that is running downwards rather than upwards. And that I had mentioned in the context of Drude formula earlier, that in Drude formula, when you have this Q square N tau over M, that N for valence bands really should be interpreted as the number of the empty states. Anyway, so I guess what we have showed here is that this N of P that comes simply from counting states, no energy momentum relation involved, that N of P, you could combine it with the energy momentum relation to get an N of E, and that would be like the electron density, which you can average over energy to get this measurable electron density. So that brings us, kind of introduces this electron density into our discussion. And what we really want to do after this, to finish up this discussion, is connect this new perspective to the old perspective, or the Drude formula. You see, the Drude formula had conductivity expressed in terms of electron density, whereas the new perspective, we have the ballistic conductance. And as I discussed, there is this correspondence. The role of electron density is played by the ballistic conductance, and then you have the mean free time and the mean free path. And in order to connect these, we needed an expression for electron density so that we can compare. And that's what we obtained in this lecture. What we'll do in the next lecture is connect the two. Thank you.